Hello, good afternoon. Thank you for inviting me to the Protochips Flash Talk, and I hope this presentation inspires you to the relevant researches with the gas phase in situ TEM experiments. Today's presentation will cover our most recent publication, which was just released at the Nature Communication, and the title today is Formation Mechanism of High Index Faceted Platinum Bismuth Alloy Nanoparticles by Evaporation-Induced Growth from the Metal Salts. Nanoparticles having regular facets in general have many advantages over the randomly shaped nanoparticles. These nanoparticles can have high index facets, which the normal nanoparticle can barely have, and show high catalytic performance on the certain reactions. The work from one of the leading group, Professor Chet Merkins, have developed a whole library of these different compositional tetrahexahedral nanoparticle catalysts, which covered with 210 facet with their unique synthesis method. Also, the research showed that the particles' catalytic activities, such as formic acid reduction, can be as high as 40 times than the conventional platinum nanoparticles. These particles are usually created with the solid-state synthesis via alloying and de-alloying process. The conventional wet method involving specific ligand chemistry is only suitable to the few material system, and after synthesis, elimination of the ligands which binds to the activation site after the production is very hard. This removal of the ligands can be done by the high temperature annealing process, but since the high index facet is thermally unstable, so that they are likely to reduce into their original low index facet. The alloying de-alloying method, which we have studied in this work, is developed a few years ago, and compared to the conventional method, it is ligand-free and can be adopted to a wide range of material systems and their precursor status. The key point of this process is the facet stabilizing effect of the foreign element at the surface of the nanoparticle. Therefore, the alloying of the two elements and the later segregation of this element is crucial. However, this process is occurred within the tiny nanoparticles at high temperature during the short period of time, so that the elucidation of the detailed process is yet unavailable. We have studied the process of generating the solid-state high-index faceted nanoparticles with the Protochips Atmosphere in situ gas cell solution. Enabled with the reductive gas flow environment and the high temperature heater capability, we have simulated the full reaction condition in situ, from the salt metallic precursors to their alloyed stage at 600 degrees Celsius and de-alloying at 1000 degrees Celsius. As you seen in these HOTIF images, first at the room temperature after it dropped, there is only amorphous salt-like contrast and no visible alloy seed. After heating the membrane to 600 degrees, tiny nanoparticles seed start to form at the location, and at the 1000 degrees Celsius, they are coarsened with each other and form larger particles. The generated particle after the whole process is well agreed with the projection images of the tetrahexahedron shape at their zone axis, which I will show you later. The below schematics and the plot shows the experimental conditions and steps. From now, I'll briefly explain how the nanoparticles evolves at each step one by one with the in situ movies. The first step of the high-index faceted nanoparticle synthesis from the salt precursor is namely seeding of the nanoparticles. When the precursor platinum hexachloroplatinate and the bismuth chloride salt is heated, first we can see the part of the salt is reduced from the 120 degrees, and then completely amalgamate at 600 degrees Celsius. Correlating with the thermogravimetric analysis, TGA, the first nucleation from the salt is from the reduction of the bismuth, and later platinum is reduced to form a solid alloy. Since there are two distinct stages of seed nucleation, we can predict there is two phases within the particle, and as you can see in the bright field, we can see distinct two different subdomains in the nanoparticle seeds. And we find that their composition is slightly different, which is one is bismuth-rich alloy and other one is the platinum-rich alloys. After the seed nucleation, we have elevated the membrane temperature to 1000 degrees Celsius to observe the second stage of the nanoparticle evolution, which is the coalescence. The previously generated nanoparticle seeds are randomly faceted and having irregular shapes. As the temperature gets higher, the tiny nanoparticles start to vibrate, and some of them moves quite vigorously. During the vigorous motion, they behave like a liquid and scavenges other particles along the pathways. We track the position and the size of the nanoparticles during the coarsening stage with the MATLAB code to remove the bias. We observed that as the particle gets bigger, average speed of the particle gets increased, which might imply that they become somewhat dynamically unstable. And after it reaches to the certain size, the particle always stops the moving and start to develop facet at their anchored position. This might conclude that the faceted nanoparticle reached to their somewhat dynamically favorable stages. Let's have a closer look to the morphological change at the individual particle after the coalescence. When the particle size grew to their critical size, the particle motion stops, and the stopped particle firstly form isotropic and spherical shape, which is usually referred as the combination of the low index plane. And then within the time scale of 30 seconds, it starts to form primitive face with the round corners, and this round corner further developed to very sharp corners, which identified as 210 facets. We have studied the stages of morphological change with the density function theory. We set the initial stage of the particle evolution with the homogeneous bismuth distribution within the whole particle, and then built an Wolf construction to estimate the particle shape. Then we moved the bismuth atoms toward to the nanoparticle surface, gradually to simulate the outward diffusion of the volatile element. The simulation result yield us that the average surface energy of the nanoparticle became smaller when we moved the bismuth out from the bulk, which means that the outward diffusion of the bismuth atom is stabilizing particle. Also, among the facets, 210 facet become more stable, while the other low-index facet become highly unstable. The resulting Wolf shape changed upon the bismuth segregation shows that the round-cornered particle observed during the in situ morphological change was the combination of 110 facet and the 210 facet. And finally, after 75 of bismuth is migrated toward the surface, the particle morphology can become tetrahexahedral shape, which is solely covered with 210 facets. To show the experimental evidence of the bismuth migration, we did an elemental quantification inside of the nanoparticle. Unfortunately, the most famous TEM-based elemental analysis does not work with our purpose. ELSE is simply not plausible since they are both very heavy elements, and also their characteristic X-ray spectrum is so close that they easily converge together. If there is distinct domain that have either one element is significantly higher in contents, like previously shown in the seed, EDS might work, but it turns out to be not working like shown in the EDS line profile shown on the left side. Instead, we have made a fine probe of the nanoparticle surface with the FIP and ran atomic probe tomography. The reconstructed model now well describes that there is a distinct segregation of the element at the nanoparticle surface. The bismuth elemental concentration at the top of 10 nanometer particle is 10 nanometer of the surface is 40%, while the 60% is being platinum. However, the bismuth concentration inside of the remaining part of 1 micron, around 500 nanometer particle, is significantly drops to 10%. This result directly shows that there were elemental segregation was happened during the facet development. This is the summary slide for the formation mechanism of the high-index faceted platinum bismuth alloy nanoparticles by evaporation-induced growth from the metal salt, which is identified with the in situ gas experiment. The initial metallic salt precursor forms nanoparticle seed below 600 degrees and alloyed together at the higher temperature. At 900 to 1000 degrees Celsius, which is the de-alloying temperature, bismuth start to segregate and diffuse out from the alloyed seed, causing instability and the particle movement. During the merging process, the bismuth continuously diffuse out and coalescence until it reaches to the critical size. Finally, the internal bismuth depletes and the 210 facet become the most thermodynamically stable facet, resulting in 210 phase covered tetrahexahedron. Let me finish my presentation with the conclusion slide. In this project, we successfully implemented alloying-dealloying synthesis of the high-index plane-covered platinum nanoparticle to the gas cell in situ TEM. We observed the homogeneous seed formation at the alloying step, and then coarsening of the nanoparticle at the elevated temperature. And as particles get bigger, they become thermodynamically unstable and start to develop facet. During the facet development, we can observe several intermediate shapes composed with the low index facet, including sphere and the round cone particle, to the finally tetrahexahedron, which is solely covered with 210 facets. The driving force of the overall reaction turns out to be the segregation and the outward migration of the bismuth. And this is my acknowledgement slide, and thank you for watching.